Bismillahirrahmanirrahim, dear students. Welcome to the Electrical Engineering channel. In this lecture, I will discuss computer-based automatic generation control. And in order to understand computer-based automatic generation control, you have to understand this block diagram. And in this block diagram, you can see several blocks. Here we have scheduled net interchange. This is actually PS. Here we have actual net interchange, which is equal to PA. Here we have tie line information processing and tie line monitoring. This block is connected with this block and it will pass out tie line loading data and compute penalty factors. These penalty factors of individual generating units will be computed over here, and the data of non-conforming loads, P coefficients or transmission loss coefficients will also be fed to this block and fixed plant generation. For example, we have some power generation types whose output cannot be altered. So those generation information can also be input to this block. Here we will calculate the frequency bias, and the area control error will be calculated over here. And area control error is actually equal to PA minus PS minus 10 BF FA minus FS. Here PA is actual net interchange and PA is positive when net power is out of the area. So net power, if going out of the area, then PA will be positive, and PS is a scheduled net interchange. PF has units of megawatts per zero point 0.1 hertz, and BF can be defined as the change in power responsible for a frequency deviation of zero point 0.1 hertz. So this is the definition of BF. Frequency bias is mathematically equal to 10 BF into delta F. So area control error actually involves the difference of these two powers, actual net interchange and scheduled net interchange, minus this frequency bias. Sorry, so minus 10 BF FA minus FS. So delta F is equal to FA minus FS. And this area control error is evaluated in the units of megawatts. Negative area control error means area is not generating enough power to send the desired amount out of the area. So this area control error is calculated over here, and you can see this is PA, right? This is PA, this is PS. So PA minus PS will come over here, and here we will have FA minus FS, which is equal to delta F, and that delta F will be multiplied with 10 BF frequency by A setting, and here we have 10 BF delta F, and that value is subtracted from PA minus PS, and then we will get area control error at this point. Similarly, another term is called station control error, and station control error is the difference of total actual generation minus total desired generation. So this is station control error, and we will evaluate the difference between these two errors, and that will give us the error signal, and that error signal will be fed to this block, and this block will adjust the area lambda, and area lambda will be fed to this block, and this block will control the individual plant generations. So this will compute assigned generation, and it will also get the information from this block, which is computing the penalty factors, and the output of that desired generation will be fed to this block, and this is the actual generation. Ideally, the desired plant generation and actual generation must be equal so that station control error is minimum. Similarly, area control error should also be minimum. And you can see here we have control signals to the plants. If we have some difference between desired generation and the actual generation, these control signals which are going to the plants, they will adjust the actual generation such that it becomes equal to the desired generation. So when these generations become equal, we have zero error, and at that point, the values of these lambdas, penalty factors, will be stabilized. So the system will run on those computed values of lambda and penalty factors. and the system will go on running. As the load changes, either in the positive or the negative direction, these control signals will change, and the whole system will work to find the new stable values of uh, lambda and penalty factors such that all the errors become minimum again. So that is how this computer-based automatic generation control framework works, right? So station control error is actually the amount of generation of all the plants minus the desired generation. Comparison of area control error and station control error. If both area control error and station control error are negative and equal, the deficiency will be equal to the excess of the desired generation. So if both these areas are negative, it means the desired generation is higher, but the actual generation is less. So in that case, at point 11, the control signals will force all the plants to increase their output power so that the desired generation and actual generation both become equal, and the errors become minimum again. Deficiency will be equal to the excess of the desired generation and no error signal will be produced. However, at position 11, a control signal will be produced for the plants to increase their generation and reduce station control error and area control error. So this is how this system works. And the important point in the understanding is that if both these areas are negative and equal, the desired generation is greater than the actual generation, and the desired net interchange is greater than the actual net interchange, but still we get zero error at this point. So in that case, the control signals generated at this position 11 will force the plants to increase their generation such that both these areas become equal. Right? So this is how computer-based automatic generation control system works. Now I will solve a very important problem on calculating the area control error and net interchange powers between adjacent areas. And in this example, you can see we have three areas, area A, area B, and area C. And this is our area A. And this area has a net generation of 12,800 megawatts and a total load connected to it as 12,800 megawatts. This is area B, and this area also has a net generation of 10,100 megawatt, but the load is 9,600 megawatts. Out of the surplus 500 megawatt power, 100 megawatt power moves towards area A and 400 megawatt power moves towards area C. And this is area C, and this area has 4,620 megawatts generation, and the total load of area C is 5,120 megawatts. So this area has a deficiency of 500 megawatts, and that 500 megawatts is actually coming from area B and area A. And area B is sending total 500 megawatts, and 400 megawatt is coming directly to area C, and the remaining 100 megawatt moves towards area A and then from area A to area C. So overall, area A has net interchange of zero, right? It is accepting 100 megawatts from area B and it is delivering 100 megawatts to area C. So net interchange of area A is equal to zero. Net interchange of area B is equal to 500 and net interchange of area C is minus 500. So we are also given the rated values of the base, right? Base kVA and the rated value of the droop curve, and RAU is equal to 0.02 per unit, RVU is equal to 0.0125 per unit, and this is the slope of the droop curve in per units, and RCU is equal to 0.01 per unit. So these values are given to us, and we can easily calculate the deviation in the system frequency as a result of the load changes or the generation changes. Okay. So each area has a load level equal to 80% of its rated online capacity. Area C is importing 500 megawatt from area B and 100 megawatt of this interchange passes over the tie lines of area A, which has a zero scheduled interchange of its own. Determine frequency deviation and the generation changes of each area when a fully loaded 400 megawatt generator is forced out of service in area B. So we are given that 400 megawatt plant in area B has become out of service because total generation in area B is 10,100 megawatt, and this 10,100 megawatt is being generated by several small generating units, and out of those generating units 400 megawatt generation has become out of service, right? So now we have a net deficiency of 400 megawatts. Okay, so it means the frequency of the system should decrease, right? So even if the load changes, the overall system load increases, the frequency decreases. Or if the overall generation decreases, again the system frequency will decrease. So the effect of load increment or the generation reduction is the same. If the generation reduces, the frequency decreases, or if the load increases, the frequency reduces. Similarly, if the generation increases, the frequency increases, or when the load decreases, again the system frequency will increase. So in both cases, the system frequency will decrease, and we are given these values of BFA, BFB, and BFC for all the three areas. And let's calculate delta F over FR. So 400 megawatt has become out of service. So minus 400 divided by these numbers, which are given to us, will give us delta F over FR, which is equal to minus 10 to minus 3 divided by 6 per unit. And delta F will be equal to minus 0.01. We will multiply this with FR, which is 60 hertz, and we will get delta F equal to minus 0.01 hertz. It means our system frequency will decrease by 0.01 hertz. Now, let's calculate delta PGA, delta PGB, delta PGC after that incident, right? So 400 megawatt generation has been reduced in area B. So after this incident, the net powers in all the areas are calculated using these expressions. So these are the same expressions which we discussed earlier. So after applying these equations, delta PGA will be equal to 133 megawatts, delta PGB is equal to 160 megawatts, and delta PGC is equal to 107 megawatts. So this is how all the remaining working generators in all the three areas will compensate that deficiency of 400 megawatts. So if we add these three powers, we will get 400 megawatts, and that deficiency of 400 megawatts will be compensated by all the other working generators in all the three areas. Okay, so this is our new power flowing diagram. This is area A, this is area B, and this is area C. And in this figure, all existing units are also present, but they are not shown. For example, this 12,800 megawatt generation is also present over here, and an excess 133 megawatt generation is also present. So that initial 12,800 megawatt is not shown in this figure, but that is present. Similarly, in area B, 400 megawatt has been disconnected, and new generation of 160 megawatts has been added in area B. And in area C, the existing power generator is also present, and a new power generator of 107 megawatt has also been added. So this is actually not the new power generator. In fact, the other remaining units have increased their generation by 107 megawatts. And this is our new system frequency after the reduction. So initially our frequency was 60 hertz, which you can see over here. And we have observed a delta F equal to minus 0.01 hertz. So our new system frequency will be 60 minus 0.01 hertz. So that will be equal to 59.99. But by mistake, I have written 59.9 hertz. In fact, it is 59.99 hertz. Okay, so I think that is also understood by you. Now we have to calculate the area control errors of all the three areas. Area control error is equal to PA minus PS, actual net interchange minus scheduled net interchange. So this is PA minus PS minus 10 BF into delta F, right? So this is 10, this is BFA, which you can see over here. BFA is minus 1200 megawatts per 0.01 hertz. So this is actual net interchange. Actual net interchange means the interchange power after that fault incident. So after that fault incident, the excess power generation from the generator A is 133 megawatts, and from this power flow diagram, we can see that area A is receiving 21 megawatts and delivering 154 megawatts. So the net power it is delivering is 133 megawatts. So net interchange, current net interchange or actual net interchange is 133 minus scheduled net interchange will be calculated from this figure. And in this figure, you can see it was receiving 100 megawatts and it was delivering 100 megawatts. So scheduled net interchange was equal to 0. So this is 133 minus 0 minus 10 BF into delta F. So that is 13 megawatt is the area control error of the area A. Similarly, area control error of area B can be calculated as well. The scheduled net interchange of area B is 500, right? Because initially it was delivering 500 megawatts in total. 100 megawatt was moving towards area B and 400 megawatts was moving towards area C. So scheduled net interchange was 500 megawatts. And currently we are observing that the area B is receiving 154 megawatts from area A and 86 megawatt it is receiving from area C. So in total it is receiving 240 megawatts, right? So 154 plus 86 is equal to 240 megawatts. So 240 megawatts of power it is receiving and 500 megawatt is also present over here, which it is actually delivering, right? So initially it was delivering 500 megawatts and after that fault incident, it is receiving 240 megawatts. So that 240 megawatts must be subtracted from the initial 500 megawatts, right? So 500 megawatts minus 240 megawatts is equal to 260 megawatts. This is the actual net interchange and scheduled net interchange is 500 megawatts. So 260 minus 500 is our PA minus PS for area B minus 10 times BFB into delta F is equal to minus 390 megawatts is the area control error of area B. And area control error of C can also be calculated. You can see initially area C was accepting 500 megawatts, 400 megawatts from area B and 100 megawatts from area A. So minus 500. Now it is generating 107 megawatts in excess, right? So out of this 107 megawatts, 21 megawatt is moving towards area A and 86 megawatts is moving towards area B. So in total, it is 107 megawatts, which is actually delivered by this area. So minus 500 plus 107 is equal to minus 393. This is our actual net interchange of area C and scheduled net interchange of area C can be calculated from this figure. And in this figure, it is receiving 500 megawatts from other areas. So scheduled net interchange was equal to minus 500 because it is receiving. So this is minus 500 and this is our actual net interchange. So this is minus 10 BFC into delta F. And after calculating this expression, we will get 12 megawatts as the area control error of area C. So that is all about our today's lecture. and I hope you have enjoyed this lecture and understood very important concepts of computer-based automatic generation control, the frequency deviation as a result of either generation changes or the load changes, and the calculation of area control errors as a result of faults. Okay. So for watching more lectures, please subscribe this channel. Until the next lecture, it's goodbye.